Move on to the O in solid, and we're doing really well here on our progress. So the O in solid is for open closed, which basically means, again, in terms of changing the minimizing the cost of change, that classes should be open for extension but closed against modification. And in particular, because we're using a language that isn't compiled and it's harder to see those changes, we're going to say closed against modification of the source code. So here's a motivating example to show how this might arise. In my hypothetical app, I have a facility for doing reports, and I have a method that will output whatever the report is, and somewhere in the user interface, the user is allowed to choose if they want to see an HTML or PDF formatted version of the report. So immediately, like almost any time when you see a case statement of this kind that is basically dispatching to different subfunctions, this is already a yellow flag, because there's no way to add new types of reports. Like if I now decide that I want to add, besides HTML and PDF, I also want PostScript or something, there's no way to add a new report type without changing the base class that contains the report. And that doesn't make any sense, because adding a new report type should not involve changing the existing report types, right? It's strictly adding new stuff. So the goal of open-close is make it so that adding new stuff doesn't require retroactively changing an existing class. One of the reasons that it's easy to fall into this pitfall in interpreted languages like Ruby and Python is if you were doing this in a compiled language like Java, and you had a report class that kind of looked like this, and you wanted to add a behavior, meaning that you need to modify by adding another case clause here, now you have to recompile the report class to do that. And everything that depends on that compiled class is eventually going to have to be rebuilt. And that's a penalty that you don't have to pay in an interpreted language. So sometimes the pain of doing this is a little bit less evident. So it's not as bad as if you do it in a statically typed language, but it's still ugly that adding new kinds of stuff requires you to retroactively change other kinds of stuff. So that's the code smell that you're looking for is essentially having something that dispatches on one of multiple possibilities, and you know that in the future it's probable that you might want to add more possibilities to the list. So how do you fix this problem in practice? We're going to use sort of a combination of 3 different things, and that'll give us the opportunity to look at a couple of different classes of those gang of 4 design patterns. And here's the game plan that we're going to follow. And again, remember, part of the challenge here is we don't know the report type that's going to be desired until the actual runtime, right? Until execution time. So we're going to do 3 things. First of all, we're going to use one of the construction patterns called abstract factory, because that will allow us to, at runtime, create an instance of a class where we don't know in advance what the class name is going to be. And it turns out that because of the way Ruby handles metaprogramming, it has a really elegant implementation of how we're going to do that. Once that's in place, we're going to essentially apply one of these 2 choices that they're very related. Template method is one, strategy pattern is the other. They address a similar thing, which is there's a particular task you want to do, but there are variations in how that task might be done. So applying either template or strategy will give us the machinery so that now when we add new variants of how to do it, we will not have to change the base class anymore. And finally, we're going to do like an additional bonus trick, which is that we're going to realize that once we have the ability to add new formatters, actually it's going to become appealing to have formatters that are stackable. So not only having a report that's, let's say, encrypted, but also password protected. And how do you sort of add different options without having an inheritance tree from hell? So we're going to do these 3 things in this order. And the first one is, in some sense, perhaps the easiest. And we're going to do a little before and after. Okay? What I've got up here is basically the code from the previous slide. This is the code that pretty clearly has the open-close problem, because these 2 when clauses are the only 2 ways to dispatch. And what we were basically doing in this case is we're assuming that the class has an instance variable at format, and that the value of that instance variable, which we're assuming is going to be either HTML or PDF, is going to tell us what is the class of the actual formatter that we want to invoke. Here's a nicer way to do it at the bottom. Again, don't worry about the syntax here. You can look up the syntax. But what the syntax is trying to do is say, take the value of this variable as a string and look up if there exists a class whose name is that. This is one of the neat Ruby metaprogramming things. You can pull this kind of trick off in Python as well. It's much harder to do this in a statically compiled language. But basically, if this statement succeeds, then the value of formatter class will be an actual class object like HTML formatter or PDF formatter. Right? So the assumption here is at format still tells us which class we want to use, but we have to have its value essentially spelled just like one of the existing classes that implements a report format. Because once we have that, we can send to that class the message, create a new instance of yourself, and boom, there's our formatter. So you can see, and let me pause for a moment because it makes your brain hurt when you look at this if you haven't seen this kind of metaprogramming before. Okay? But again, just to review, what's going on is format is still supposed to tell us which type of formatter we want, but now we're going to ask Ruby to look up the class whose name matches that, and then we're going to tell that class, please create a new instance of yourself. That's my formatter object. Formatter is now an instance of the correct kind of thing, even though we didn't know at the time of writing this function what value at format could be. And of course, I've got a rescue clause, because if format is set to something like foobar, and there's no such thing as the foobar class, then when we try to do this, somewhere in here an exception is going to be raised because the class doesn't exist, and that lets me capture the exception and report back to the user, I don't know why, but at format is set to something stupid. Okay, so any questions about how this part works? I should say, what questions do you have about how this part works? Because the first time I saw code like this in Ruby, I was frankly confused. And I couldn't think of a good clicker question, so I'm going to rely on you to sort of speak up and say, that made no sense to me at all. What clarifications may I offer before going on how this piece works? No? OK, you're all with it, or all great. So this is an example of what's called the abstract factory pattern. Why is it an abstract factory pattern? Because you don't know at the moment you create the class, or sorry, at the moment you're writing this code, you don't know what possible value this class is going to be. You just know that at runtime, this variable at format is going to tell you that. So it's basically, I need to create an instance of a class, and the class is going to be somehow determined by something that's an input to this function, right? So this is Ruby's very concise, in my opinion, implementation of abstract factory. So that was step one, right? Now we have a way, and by the way, I think you're going to believe me when I say this now. If we now decide to add PostScript formatter, and we create a new class called PostScript formatter, then no changes are required down here. Because if this comes in with the value of that format being PostScript formatter, then this will just work. And if it comes in with that value and we have not defined the PostScript formatter class, then we'll throw an exception and handle it and say, sorry, there's no such thing as a PostScript formatter. So hopefully you believe me that by the end of this step, we're at the point where adding new possible report formatters no longer requires modifying the report base class containing this output method. If you believe that, then the next step is to figure out what mechanism we're going to use so that as we're adding those new varieties of classes, there's kind of a standardized way to do it that allows the report base class not to change. And there's two different approaches that let us do this. One is called template method. The other is called strategy. And really, the difference between them is in the template method, the set of steps for doing it is the same, but the implementation of the steps might be different in different variants. And that means that in general, you can use inheritance to implement it pretty gracefully. So for example, I'll show an example using the code from the previous slide. There we go. In contrast, if the task to be done is the same, but the specific sequencing of steps might be different in the different methods, then the strategy pattern is a little bit more general because it makes fewer assumptions about the internal structure of each of the variations. The trade-off is that the implementation is a little bit more subtle because you don't just get to use simple subclass inheritance. So I think the easy way to understand this is let me show how each of those two alternatives could be applied in our ongoing example about report generation. If we were doing the template pattern, we're basically saying, in the future, we might add new types of report formatters, but we always know that any report formatter is going to do three things. It's going to output a title, then a header, and then the report body. So no matter what other formatters we add, this is basically the structure that they're all going to have. They're only going to be different in the implementation of the methods that do each of the steps, but the sequencing of the steps will be the same. So this is pretty easy to implement because now, if report is our base class, we can just create subclasses of it that override the individual methods. Right? That's all there is to it. So if the sequencing of steps across different variants of the task is always going to be the same, this is probably the most straightforward way to do it. And the only machinery required is you're just doing inheritance from a base class. But there's a lot of situations where this is not sufficiently rich. Oh, by the way, if you care about doing these class diagrams, this is what the class diagram looks like. Right? Here's our base class. These are both inheriting from it. And the inheritance just allows each of the subclasses to do whatever specific thing it wants to do to override these generic methods. In the purest case, these methods are abstract, or I should say this class is abstract. And if you're using a compiled language, you can actually say the report class itself cannot do any of these things. These are purely virtual methods or purely abstract methods that must be overridden. In Ruby, you can't, there's really no way to say that. So what some people will do is that in the base class, they'll define these three methods, but the methods will raise an exception saying, I should never be called, because the reality is some descendant of me in some subclass is what should be called. Okay, so that's what this looks like. This is the simplest possible way to do it. What about cases where this doesn't work because the sequencing of steps is not necessarily the same? Maybe there are some report types where these are not the same three steps, or where they're not done in this order, or where some other thing has to be done. So the more general version of this is the strategy pattern, which basically says the report base class is not going to have descendants. Instead, one of its attributes is going to be a formatter object, and that formatter object may have some subclasses. But I don't really know anything about how the formatter object works. Right? So when someone calls output report on an instance of the base class, all it does is delegate that call to one of its subclasses. Right? So when we did the abstract factory pattern, we showed how you can arrange for the report's formatter to have the correct class at runtime. Basically, the report is saying, the only thing I know how to do for output is essentially forward that request to whichever formatter was chosen. And internally, I have no knowledge of what it does. There's no assumption that all formatters would work the same way. And on the next slide, we're going to see if you end up having to do it this way, there's actually another nice benefit that you get. So there's this general principle that says when you're trying to isolate things that change from things that stay the same, yes, it's true that when you're using subclass inheritance, that is one way to reuse behaviors. But there's a number of different issues that come up. One of them, which we're going to talk about in the next solid, which is Liskov substitution. But also, it's pretty rigid. Right? The inheritance actually makes a lot of assumptions about the similarities between a base class and its subclasses. Here, we're not really making any. We're just saying the report knows that it has a formatter associated with it. And when it's asked to do something, all it does is delegate it. It forwards the call to that formatter without any assumptions about how the formatter is going to do its job. So let's see what else you can use this for. Because, continuing the motivation of our example, imagine that we want to enhance the PDF formatter in the following way. As you may know, a thing that you can do with a PDF file is that you can protect it with a password. Another thing you can do with a PDF file is you can watermark it. It's the equivalent of having those draft, do not reproduce. And in fact, you could have any combination of these features on a PDF file. So suppose you wanted to expose something like that. What's the right mechanism for doing it? Because if you try to solve this with inheritance, you start to run into a problem. Right? We already have the plain old PDF formatter. But now we need a PDF with password formatter, a PDF with watermark formatter, and a PDF with password and watermark. And if the order in which they're applied matters, then actually we would even need another one, which is a PDF with watermark and password formatter. So you start getting an explosion of behaviors. Right? And it smells bad to sort of try to make a separate subclass for each of those. So inheritance doesn't solve this problem particularly well. But the previous approach, using the strategy pattern, actually can solve it quite nicely in the following way. And I'll show the source code for this in a moment to help you walk through it. But conceptually, here's what's going on. We have an existing PDF formatter, but we're going to define these additional classes that we say decorate the behavior of their superclass. So what does it mean to decorate a superclass's behavior? It means that each of these subclasses will have as one of its components a copy of the object to which it belongs. It has specialized behaviors that it knows how to do, like adding a watermark or protecting something with a password. But the thing that it returns as a result of those behaviors is an object that is compatible with the base class. And again, let me show the source code will make this a lot easier to understand. So let me show you what that looks like. Okay, now we're getting, this is like good refactoring software engineering stuff. So what do we have going on here? At the top, here's our generic PDF formatter. The only thing it knows how to do is it can be one of the kinds of formatters that you'll delegate a call to, and its output method will get called. Now let's decorate it. To decorate it with the ability to do passwords, notice that although I'm inheriting from the superclass, my constructor is different. In particular, when I construct an instance of PDF with password formatter, it is expecting to be passed a copy of the class that initialized it. Because then, when I call output, basically what I'm saying is, when I am called upon to do to add a password to a file, the first thing I'll do is I'll call the output method of my base class. That's this method up here. Then I will protect that thing with a password, and that's the thing that I return. So I'm essentially delegating most of the work to the class I inherited from, but I'm doing my little special bit of magic on top of that basic work, which is where the name decorator comes from. Let's do a different decoration. Same idea here. PDF with watermark formatter. When I am called, I will retain a copy of the object that owns me. And when I'm called to actually do some work, I can first delegate most of the base work to be done with my original class, with the object that owns me. And then I will add my little special function of watermark on top of that. And what's really nice about these is that they can be stacked up, right? Because I can create a new PDF formatter. That was the basic one we already had before. And now I can create a new PDF with watermark formatter that takes as its constructor argument a regular PDF formatter. So these two classes have the same class signature, right? PDF with watermark formatter is a subclass of PDF formatter. So anywhere that it's legal to use one of these, it is legal to use one of these. We'll talk about that more in detail later. That's called Liskov substitution. But intuitively, I think you get the idea, right? Every instance of PDF with watermark formatter is also an instance of PDF formatter. So, but now, once I have this formatter, I can actually also stack it 3 deep, because anything that is a valid subclass of the base class can be passed in as the constructor. So now I can start with a PDF formatter, decorate it with password addition, and decorate it again with watermarks. And the thing that I still have, the formatter, is still something that could be called anywhere that PDF formatter could have been called. So from the point of view of who's doing the call on the formatter, it behaves the same way. It has an output method, but I can stack the decorators in any order that I want. Right, so that's kind of how the source code looks for an example like this. And we say that these classes decorate the behavior of a class that is Liskov compatible. In a few minutes, we'll talk about Liskov substitution and what that formally means. So, by the way, you may have already seen this, depending on how much complex code you've written in Active Record. If you've used Active Record scopes, or even if you remember some of the simple Active Record examples we did at the very beginning, that you can define a scope like for kids, which basically translates into where rating is G or whatever we said it was. And you can define a scope like with good reviews, which looks for a movie whose average review score is whatever. And now you can actually stack all of these. You can chain them in the calls, right? You can chain the where calls. So this is actually an example of doing decoration, where you can create scopes that decorate the basic behavior of the active record relation, and then you can stack the scopes as long as anytime you stack them, the stacking observes the fact that any one of these could have been legally called wherever you expected a movie. So if you can call where on a movie, it has to be possible to call where on whatever is returned by for kids, and it's got to be possible to call where on whatever is returned with good reviews. But if you maintain that, right, and that's kind of what we did in this example, all of these guys have an output method, but they expect to be able to delegate some behavior to their containing class. If you can get away with that, then you end up with these nice stackable decorators. So we've sort of applied 3 different mechanisms here. And again, inheritance plays a role, but the more important role is the one played by composition. Right? Composition just means one of the components of some object is an instance of some other object to which some work is going to be delegated. So a careful use of this stacking, right? Again, what were the 3 things we did? We made it so that the abstract factory can be used to create the correct class of thing at runtime. Now we don't have to change the report class anymore. Then, using either the template method pattern or the strategy pattern, we defined what the interface of any formatter has to be. It has to have this output function. And then finally, if in fact we're using the strategy pattern version, we can also take advantage of the fact that we can define subclasses that do decoration and then are stackable on top of it. Right? So that's, I kind of like this example, even though it's a little complex to get your head around, because it illustrates 3 different design patterns at work. Right? There's the abstract factory pattern, the template pattern or strategy pattern, whichever one you use, and then the decorator pattern. And they're all sort of put together in the service of solving what is a realistic problem. So in practice, right, open-close says don't make it so that classes are closed against modification. And the problem is that that sort of simplistically assumes that you somehow know in advance all of the types of changes you might someday want to make. And of course, that's an ideal, but in practice, you don't necessarily know. There's no real magic bullet. Sometimes you'll find yourself in a situation where you just did not foresee that there was a particular way that you wanted to extend a class. Right? When you create examples for instruction, you can always create an example where it makes sense to say, well, yeah, of course, you might want to add new report formats in the future. But what if what you really need to add is within the PDF format or different printer types or character sets? There isn't really anything in the interface we described that would make that easy to extend. So sometimes you actually won't know what the answer is, but the idea that if you're doing scenario-based development with your users and you sort of get an early signal about the kinds of things they might want to do, no magic bullet here, but it's a way to try to identify early on the things that plausibly might want to change in the future. So again, these are all best effort things. You'll not find yourself always getting them right the first time. So you can try to close against the types of changes that you're pretty sure are going to be extensions you want in the future. Sometimes you'll miss. That's life. Summarizing, open closed. Where are we? It says that if you're extending the functionality of a class, maybe by adding additional variants of what it can do, that should not require modifying any existing code, just adding new code. And what can you look for as a yellow flag that you might be doing this? Well, the canonical version is something like that I showed, which is whatever set of ways there are to do something, somewhere in your code there's basically a hardwired multi-way dispatch that picks one of the ways. That means that if you need to add a new way, you have no choice but to go somewhere into that dispatch function and start adding clauses to it. And again, it's easy to sort of creep into this without realizing it, because if you were doing this in a compiled language, every time you have to add something, you've got to recompile. And now all the other developers who depend on your library are being notified that they have to relink against your newly modified library, and then they hate you. But here, that never happens. So what can you do if you find that you have this problem? In our example, we applied a couple of different things. We started with abstract factory because that lets you essentially not need to know at runtime what all the possible values are of the variants, as long as you have a class that can implement each one of them. Then we decided, depending on the kind of task you're going to do you try to capture it as a template method? So you have a superclass that does a fixed set of things, but then you've got subclasses that override the implementation of each step. Or is it more general and you try to just capture it as a strategy, which means you have a component in the base class that says, I am an example of a formatter. You can call output on me, but don't make any assumptions about the internal sequencing of steps or anything like that. And then we also saw that if you go that approach, it gives you the possibility of also adding incremental behaviors and sort of stacking them up on top of the base class. Right? Not every example will necessarily have all these properties, but that's kind of our summary.